ultimately, we would like to be able to have a comparison of skeletal muscle, smooth muscle, and cardiac muscle to see how they're similar and how they're different. We'll focus on cardiac muscle in great detail when we study the cardiovascular system, and we'll start that on Friday. But for now, just for comparison, let's look at an extreme comparison to skeletal muscle, and that's smooth. And why I say it's an extreme is structurally, they share very, very little in common, right? Smooth muscle is not striated. There aren't sarcomeres. There's no troponin. There's no tropomyosin. What they do have in common is that they have actin and myosin. They do overlap, but they're not arranged in sarcomeres. And the muscle cell membrane, the sarcolemma, is excitable, meaning it can generate an action potential. And there is some calcium stored inside of the cell and sarcoplasmic reticulum. So those are the similarities, but they're very different. Now, what I want to show you as a comparison is this smooth muscle excitation contraction coupling. How does smooth muscle contract in comparison? I'll point out that smooth muscle is a lot weaker than skeletal muscle because it doesn't have nearly as many potential cross bridges that can form. The time for the twitch, like that over there, is way longer than it is in skeletal muscle. So they're slow to contract, they're slow to relax, and they're weaker. Now, I just highlighted a couple differences here. Smooth muscle excitation contraction coupling involves the influx of some extracellular calcium. Now, in skeletal muscle, all of the calcium that was responsible for triggering skeletal muscle contraction came from where? Who studied this weekend? Where's the calcium come from in skeletal muscles to trigger contraction? The SR, right? Sarcoplasmic reticulum. All of it. None came from outside. So here's a difference. Some of the calcium comes from extracellular sources. There's no troponin, no tropomyosin, so calcium's not going to bind to troponin and displace tropomyosin, etc. What's going to happen is that calcium is going to trigger a cascade. And remember, cascades are common in physiological processes. A happens, then B happens, then C happens, and then you get contraction. Okay? Now this cascade involves two compounds that we haven't probably talked about before. Something called calmodulin, and then there's something called MLCK, which stands for myosin light chain kinase. Now its name tells you exactly what it does. What is a kinase?
Something that puts phosphates.
Something that puts phosphates on proteins, right? And remember, phosphorylation of proteins is a way to activate and inactivate proteins, right? Okay. So here, myosin light chain kinase puts a phosphate on the light chain of myosin. So it phosphorylates myosin. So when myosin is inactive, there's no phosphates on it. When myosin light chain kinase here puts a phosphate on myosin, so myosin phosphate here, right? So I just stuck a phosphate on myosin, it becomes active. And as soon as it's active, what does it do? Binds to actin, you get contraction. That power stroke cycling will continue as long as myosin's phosphorylated. How do you do relaxation? You have to use a phosphatase. What's a phosphatase? It removes phosphates from proteins, right? To take the phosphate off of myosin, to make it inactive again, and then the muscle relaxes. Does that kind of make sense?
Mm-hmm.
Okay, so this is very different, right? We have myosin and actin right next to each other, free to interact, but myosin doesn't have an affinity for actin unless we put phosphates on it. And as soon as you put phosphates on it, the affinity is really high. You go from 90 to 45. The power stroke cycling is the same with the binding of ATP to break the cross bridge, hydrolyze ATP to repocket it, and all of that. All of that's the same as long as there are phosphates. You okay with that? All right. So that's a little bit different. Okay. And then what we'll see, what's really cool, is when we finally get to